use one of your scientific calculator? One of the students does a scientific calculator.
I'm missing one. Who knows?
Is that right?
No,
Oh.
scientific, not graphing.
Oh, gotcha.
Okay, so we are in the mix of talking about 5.4, in the mix of talking about concavity and second derivative test is where we're headed. Okay, now we were talking a little bit about concavity. Remember, a point of inflection is where concavity changes from concave up to concave down or vice versa. What we're going to talk about here is talking about the possibility that a graph could change concavity at a discontinuity. Okay, now, if a graph changes concavity at discontinuity, that doesn't necessarily mean inflection point. Okay, it could be inflection point, but if there's a discontinuity, then again, it also very strongly won't be. So we're going to talk about some cases here. These left cases, okay, here is a scenario where P represents an inflection point. Okay, my graph clearly changes from, on the left it is concave down, to the right it is concave up. And that P is an example of where that is happening. And this is a scenario where the second derivative would be equal to 0. Okay, so if that second derivative is equal to 0, thus we have a critical point of your second derivative, which is usually an inflection point. Okay, this graph below it is also an example where we talk about inflection point. It just looks totally different. Okay, my graph is still continuous. Technically, it's not differentiable there, but here we change from, if you notice over here on the left, this is concave up because it's curved up, to over here on the right, it is concave down where it's curved down. Okay, so that is a scenario where it is also an inflection point, but here the second derivative at P would not equal 0, it would be a DNE. It does not exist because we've got that point that's not differentiable. Okay, so you can't take a derivative at that point, so the derivative is not going to equal 0. So those are two cases of inflection points. Okay, and we're showing you that concavity changes there. Now, over here, these are some cases of no inflection points. For instance, on this one, notice the left side is curved up, so it's concave up. What about the right side? It's also curved up, concave up. So at P, we can't talk inflection point because the concavity doesn't change. An inflection point is where your concavity changes. Now, this would also be a scenario, though, like our previous one, where the second derivative doesn't exist. And again, the second derivative would not exist because you've got a cusp or a sharp point that we can't take the derivative at. Okay? So there's a situation. Concavity doesn't change, not an inflection point. And this is the other one. At P, there is a discontinuity, right? So here, curved up on the left, so concave up there, curved down on the right, so concave down there. Concavity changes, but there's no inflection point because it's a discontinuous graph at point P. Okay, so yeah, the curves are different, but this is x equals P is a vertical asymptote. And with it being a vertical asymptote, you can't have a point of inflection there. This would be another one where the derivative at P does not exist. Okay? Are we okay with those graphs? Those are supposed to be pretty basic. Are they pretty basic to you guys? Or is that just in my mind?
it can have an inflection point without having a second derivative necessarily because of the second one.
Yes, because like that's a sharp point that you technically can't take the derivative at, but by definition, concavity changes. So it's not, I would say about this one, it's not your typical inflection points.
Gotcha.
Your typical inflection point is this scenario up there, where it's a typical continuous curve, and the way the curve changes, it changes concavity. This is the oddity, in my brain at least. Okay. Okay. We're going to talk about a second derivative sign chart to determine intervals of concavity as well as actual inflection points. The possible points of inflection are your critical values. Okay, and that should say critical values of the second derivative there. That's a typo and just says first derivative. Okay, the critical values of the second derivative are your possible points of inflection. You'll sometimes see those as PIP, possible inflection points. Okay, now concavity can change in a discontinuity. We just talked about that, such as a vertical asymptote, but it won't be an actual inflection point. In order to classify an x value as an inflection point, the x value must be in the domain. Okay, so like that vertical asymptote, we wouldn't have been able to classify that as a point of inflection. So we're going to start talking about how to use this second derivative test here. Sorry. In order to talk about the second derivative, we need to find the second derivative. So, what's the first derivative? Okay. 4x cubed minus 12x squared. We could set that equals 0 and talk about critical points, but we're talking about second derivative test here. So, what's my second derivative?
X squared minus 24x.
Okay. So, in order to find our critical points of the second derivative, of course, we're going to set that equal to
Sure.
0. We okay. GCF of 12x.
So x equals 0 and 2.
Okay, so yeah, you have a factor of 12x to set equal to 0, and a factor of x minus 2 to set equal to 0. So yes, we get critical points at 0 and 2. So I'm going to go that over here and put these on my number line. Okay, so these are my critical numbers. Now, I want to know what's going on in each interval. And as we talk about what's going on in each interval, pick some test values. Okay? And as we pick test values, again, we're trying to figure out, these are critical values of the second derivative, what's going on with the second derivative. My recommendation is you use the factored form. I know Logan disagreed and didn't always want to use that, but it's to each your own. You want to know what's going on in each of these intervals. So if I pick a value left of 0, for instance, if I test, say, -1. For me personally, 12 times -1 is a negative. -1 minus 2 is a negative. And a negative times a negative is a positive. Okay? Same thing between 0. Or between 0 and 2. Between 0 and 2, I personally would pick to test 1. 12 times 1 is going to be a positive. 1 minus 2 is a negative. And a positive times a negative is a negative. And then if I pick a value larger than 2, I'm going to pick 3. 12 times 3 is a positive. 3 minus 2 is a positive. Positive times positive is a positive. Now, what does this mean? When my second derivative is positive, those intervals are going to be what? Concave up. When my second derivative is negative, it's going to be
Concave down.
concave down. Okay? So concave up, concave down. Hopefully you're catching on. I'll either use CU and CD for concave up and concave down, or basically a parabola for concave up or concave down. Now, what information did we gather here? What was the question actually? Determine any points of inflection and discuss concavity. What points of inflection did we have?
0, 2.
Okay, points of inflection occurred at 0 and 2. And how do we know for sure they're points of inflection? Because concavity changed, yes? If concavity doesn't change, they're not points of inflection. But concavity changed. Now, the way it says that, points of inflection, it doesn't say where are the points of inflection, as in they're at x equals 0 and x equals 2. It's more what are the points, so more like ordered pairs. So what I would say there is that we should probably give the whole point. So I'm going to say points of inflection.
0, 0, and you plug it in the original, don't you?
Yes.
So that's going to be 16 minus 4 times 8, so negative 16.
Yeah.
For
Okay.
some reason, when I did x to the third, I was thinking 4 to the third, and I got 64. I was like, wow, that's really big. And I got
Okay, so points of inflection, they occur when x equals 0 and x equals 2. I wrote those as f of 0 equals 0, and that would be plugging into the original problem, because that's where your points are going to come from, is the original problem. So you plug in 2, and you get negative 16. The other thing they ask us is to discuss concavity. And so
we concave up from negative infinity to 0, and concave down from 0 to 2, or negative infinity to 0 and 2 to infinity, and then it's going to be concave down from 0 to 2.
okay. So intervals, yes. I was looking to see, yeah, f of x is concave. I started with up, and that is going to be the negative infinity to 0 and 2 to 0. Why is it concave up there?
Because the second derivative is greater than 0.
Okay, so your AP reasoning here is because second derivative is greater than 0. We can write a similar statement that f of x is concave down on the interval 0 to 2. And my reasoning there is that f double prime of x, the second derivative, is less than 0. Okay?
Would it be a bracket or keep it in parentheses?
Parentheses, because they're not touching it.
Parentheses, because at the points 2 and 0, those are inflection points. So the graph is technically neither concave up nor concave down at that point.
Gotcha.
Okay? Kind of like when it's a 0. It's not positive, it's not negative, it's 0. Okay? Okay. Let's go ahead and talk about 4. I have to figure out which ones. And as I said, I have several noted in my notes that we're going to skip. So, okay, 4. Ask us to find the inflection points and open intervals of concavity and to justify. Part of the reason we're doing this one is we got to review our trig. Okay? So, part of the reason I'm not skipping it. Inflection points and concavity means we need to get to our second derivative.
Be just negative sine x.
Well, I'm still back on the first derivative. First derivative is 1/2 plus cosine x, yes?
Yep.
Second derivative, did you say negative sine x? Okay, I'm caught up now. Are you caught up, Eli?
Yeah.
My brain was just thinking so. Okay, what do we need to do? Set this equal to 0. Now, negative sine x equals 0. Personally, I would divide the negative out of there. In other words, we can think it's going to be the same statement to say sine of x equals 0.
It equals 0 at, what would it be 0 and pi, or pi and 2 pi.
So what numbers do we need to give? We need to give anything on the closed interval, 0 to 2 pi. Which means we need to give 0, pi, and 2 pi.
They're the same point.
Technically, they're on the same point in the unit circle, but on a graph itself, no, because remember the graph goes on infinitely. That graph oscillates infinitely. So they're not physically the same point. Are you okay with those points, Eli? I can't remember. Do you do the graph or you do?
Graph.
You do the graph. Okay.
Sometimes. Depends.
Depends. Fair answer. Okay, but you were okay with those?
Yeah.
Okay. Because if not, I'll go over them by all means. Okay. Now, with this, we need to test it, yes? So set up a line like what we had. Now, here's the deal, guys. This is a second derivative line. My points of interest here were what? 0, pi, and 2 pi. Do I need to look past 0 and 2 pi? Normally we would, right? But I don't need to in this scenario because we're on that closed interval. And with trig functions, are always going to give you an interval to work with. Well, majority of the time, they're going to give you an interval to work with, okay? So we only need to look in those two segments. Does that make sense? So, okay, find our second derivative, and second derivative was negative sine x between 0 and pi.
I just do pi over 2 and it would be positive 1, so it'd be positive, and for between pi and 2 pi.
But what was our second derivative? Our second derivative was negative sine x.
We factored out the negative.
Okay, we did when solving, but we're not plugging back into the equation where it equals 0. We're plugging back into the whole piece. That negative has to still exist.
So why did we factor out the negative?
So here when we were trying to solve and we had an equation, we could essentially divide both sides by a -1 just to make the math easier. So we can just think, okay, when does sine equal 0? Up here, when we're trying to test on the number line, you've got to use the whole thing. Okay? And so if we're using that whole thing, we've got to use that with the negative sine x there, without the equation changing. Okay? So with that in mind, it's going to be exactly opposite what you were originally thinking, right? And here's my thing. My brain says sine is that graph right there, yes? what's a negative sine x graph going to do? It's going to take it and it's going to flip it. So a negative sine x graph is going to be exactly upside down. So from 0 to pi, it's going to be negative. From pi to 2 pi, it's going to be positive. Now, a negative second derivative means what? Concave down. A positive second derivative means concave up. What did they ask us to do? Inflection points and intervals of concavity. So what do we have in the way of inflection points?
It's going to be pi something.
Okay, there's going to be an inflection point at f of pi equals, no, I guess it's not f, it's g, but same idea.
Be, just be 0. Is that the way you go about it? Pi 0.
Now, are you plugging it into the original equation?
No. Still 0.
Pi over 2.
Plus sine of pi.
Right, which sine of pi is 0, right? So pi over 2?
Yeah, sine of pi is 0. Right?
Yeah, sine of pi is 0. But I thought you were saying the whole thing was 0.
Oh, I, for some reason, put 1/2 times 0 in my head.
Okay,
So I was like, still 0.
okay.
I had this.
Yeah.
I thought you guys were saying sine of pi was pi over 2
No.
somehow.
So yeah, so g of pi, we would have been doing 1/2 times pi plus sine of pi. So thus we went pi over 2 plus 0. I wasn't arguing that, but okay. So there's an inflection point at g of pi equals pi over 2. And why is there an inflection point there?
Because it changes from concave down to concave up.
Okay. Or I was going to say g prime of x, or seriously? Erase. Sheesh. So g prime of pi changes sign. From, what was it, negative to positive. Multiple different ways you can say it. What about concavity?
Concave up is pi to 2 pi.
Concave up from pi to 2 pi. And that's concave up because
G from x is greater than 0.
okay, second derivative is positive. And concave down, 0 to pi, because the second derivative is less than 0. Okay. 5, grab your calculators. You will need your calculator.
Grab mine too. Grab mine too.
Notice it says it's calculator active. And then notice what it says. Use a calculator to find how many times the graph of y changes concavity on the interval 0 to 2 pi. It's a number answer here. How many times does it change concavity? What are we going to have to be able to, what are we going to have to think about here?
How many times is equal to 0?
How many times what is equal to 0?
The second derivative.
Second derivative. So, before we get to the calculator, we need to find our derivatives, yes? Okay, so first derivative. Good old derivative practice here.
2x minus 1 times 2.
You guys okay with that?
Yep.
I put my 2 out front of my cosine because that's how I roll. It's good AP mechanics, doesn't mean you have to. Second derivative?
2 plus, or 2 minus, I guess.
Mm-hmm.
So, or 2 sine 2x minus 1 parentheses times 2 again, so it'd be 4 minus 4.
Mm-hmm. Are we okay with that?
Yeah.
Okay, there was already the 2 that I didn't write on purpose because I'm going to multiply by my chain rule. The derivative of 2x minus 1 is 2. That was chain rule there. Okay, so officially, yes, we're going to set the derivative, the second derivative, equal to 0. And what we want to know is how many times it changes concavity, which means what we really want to know is how many times does the second derivative equal 0. What's going to be the best way to do that on the calculator?
Oh. I was good at my hand. You just type it in the graph.
Okay, we're going to graph it.
I was stuck at sine of 2x minus 1 equals 1/2.
Exactly. This is why it's a calculator active problem. This is not a head problem. Okay. So we're going to graph it. Some recommendations I might give you is check out the Z-trig setting. And then what interval do we care about?
0 to 2 pi.
Yeah. So then after you get to Z-trig, I would change your X min to 0 and your X max to 2 pi. Do I need to do this also, or?
You can't see it, but
I know. I hadn't even turned on my elbow today, I realized, so. Okay, so I have none. I'm going to go ahead and do a Z trig, which is a 7. Now, while that graph is helpful, does it give me everything I need?
No.
No, because I don't know what's going on there. I need to know on the interval 0 to 2 pi. So I would now go into your window setting, and I would make my X max 0, and my X min 0, and my X max 2 pi, because that's the only interval I really care about. I'm going to hit graph again. And now I'm specifically looking at the interval 0 to 2 pi. How many times does the graph change concavity?
4
Why 4?
times 0 4 times.
Okay. The graph changes
There's 4x.
from positive to negative or negative to positive a total of 4 times.
Gotcha.
Okay, make sense? It seems like it's going to be a really complicated problem. It's not. It's just understanding, okay, what they mean. So the answer is 4 times. And that's because the second derivative has 4 zeros. And I guess I should specify it has 4 zeros on the interval 0 to 2 pi. Okay. Could you find those points of inflection if you needed to. Yeah, we could find the zeros. I have them written down here. It doesn't say, it just says how many times. Okay? Now, number 6 is doing the same thing. Use a calculator. How many times did it change concavity? The trick there is finding the derivative again. But I'm going to move on to the bottom here, if we're okay. And you guys know everything is online if you want to go back and look at anything or ask me later. Okay, so talking about the second derivative test here a little bit, okay? Second derivative, remember, is the first derivative of f prime. So same relationships that exist between f and f prime exist between f prime and f double prime. We can use the second derivative test as an alternative method for finding extrema, for finding mins and maxes. So generally we think of second derivative concavity, first derivative mins and maxes. However, there is a way we can use second derivative to find mins and maxes. So let's see. Just a little connection here. I think you guys had this a little bit in your notes the other day, if I recall. But if x equals c is a critical number of f of x, then two things could happen. The derivative could equal 0, or the derivative could not exist. So this makes the value c a possible max or min value of the function. Now, what does this tell me? If your second derivative is positive, what does that tell me about the original graph? If the second derivative is positive, the graph is concave up. Okay, so when it relates to, your second derivative relates to the original graph, we're talking concavity here, concave up. That also means, if we go below it, when your second derivative is negative, what's it mean about the original graph? It is concave down. Okay? What if the second derivative is neither positive or negative?
Constant?
Huh?
Is it constant?
What's probably, if it's not concave up and it's not concave down, it's probably, I wouldn't say constant.
Straight line?
Think about if your second derivative is either 0 or does not exist. What connects concavity? An inflection point. So I'm not going to say it is an inflection point, but it is a possible point of inflection. Okay? Now, let's relate to first derivative. Okay? If your second derivative is positive, what is the first derivative? And this is kind of the same idea as if we were talking, if the first derivative is positive, what do we know about the original graph? If the first derivative is positive, the original graph is increasing. So here, same relation. If the second derivative is positive, the first derivative is increasing. If your second derivative is negative, then your first derivative is decreasing. And if second derivative is neither,
Constant.
no,
D and E.
no. What would be in between increasing and decreasing?
Constant.
No, like, what points of inflection connect concavity?
Yeah.
If something increases and then changes to decreasing, that could be a max or a min. I was not getting that through, was I? So it's a possible max or min.
Which technically is constant as I have before, because its slope is 0.
True.
I don't have time to even try and dissect
I
that.
mean-
I'm there with you. I have to move on at this point, but
Using, was there roll?
okay. I want to look at 7A. Okay. And I'd hoped to look at 8, and I was probably going to skip 9. So we just might get cheated out of 8. We'll see. Use the second derivative test to find the relative extrema for each function and justify. Now, in order to do this, we first of all have to find our first derivative and find the critical points there. So, first derivative.
4x cubed minus 24x squared.
Okay. We need, hold the thought on the second derivative, or you can do it now, but
Yeah.
first of all, before I move on, I was going to go ahead and get the critical points from the first derivative. Okay? Because we still need our critical points for the first derivative, because we're talking extrema, and
But it
extrema
said
still
use the
happen at
second
critical points of the first derivative.
But it said use the second derivative.
We are going to use the second derivative test, but to find the points, we have to stop and use the first derivative there. So if I set 4x cubed
4x squared
minus 24x squared equals 0,
x minus x is going to equal 0 and 6.
okay, so those right there are my critical points, okay, or my critical numbers, whatever you want to call them. Those are my critical numbers. Those are my C values that are going to go right here. Okay? Now, with that in mind, I don't know if you want to go ahead and find it right now. They do in that first box, they do ask for what G of 0 is and G of 6 is. Okay? Eli gets G of 0 is negative 5. G of 6 is negative 437, says Mrs. Sargent. Okay? I know, but I'm also in the last 5 minutes of class. So, that's the only reason I gave it to you. Now, let's talk second derivative. You guys, I think, already found the second derivative, didn't you? Second derivative was
12x squared minus 48x.
okay. So now what I want to know, the critical values from above. What is the value of the second derivative at those?
Well, it's going to be 0.
So the second derivative at 0 is 0. The second derivative at 6, my book says 144. Oh, sorry, Logan's plugging it in. He's going to be mad at me.
Says 144.
Are you disagreeing with me? Are you plugging it into the second derivative? 12x squared, so 12 times 6 squared minus 48 times 6.
So 432, because 12 times 36 minus 48 times 6. 48 times 6 equals 144. But 432 minus 144 equals 288.
Interesting.
12 times 6 squared
Maybe I have it wrong in my notes.
minus 48 times 6. That says 144. What's the difference here? Because when you do it like that, it gives you 144.
Okay, and what did you do?
Oh, it's because I took my answer minus here.
Okay. It's 144. So I'm going to fill in over here. When C is 0, the second derivative is 0. And when C is 6, the second derivative is 144. Okay, guys. What does 144 is a positive number. What does a positive second derivative mean? It means concave up. If that is concave up, what's going to be on that graph in that interval? A minimum. Okay? So that's going to represent a minimum. Okay? What about when the second derivative is 0? Is that going to be a min or a max?
No.
No. Okay? It's a possible inflection point. We don't really know. We just don't have a conclusion on that one. Okay? So what I have written down here is that there is a local min. Oh my goodness. That occurs at x equals 6. And is, the value would be that negative 437. And that's because the second derivative at 6 is greater than 0. And thus G is concave up. And then the other piece that I was going to mention here is there is no conclusion at x equals, what was it, 0. Okay? Okay, I planned to skip B anyways. The only other part I really wanted to do was 8. You might try and look at 8 on your own. Do 5.4 homework tonight. Okay? 5.4 homework tonight, and we can talk tomorrow and go from there. Okay?
Yep.